All right. So, on our reminders slash things to do, 1, group quiz today. Good. 2, your next mastering is due after spring break. And then your exam is a week after spring break. So it's not the Monday you get back, it's the Monday following that. Alright, so we started this problem on Wednesday, right? We looked at the pH when we've added 50 mils of hydrochloric acid to 50 mils of 0.1 molar sodium hydroxide. I want to look at some other points that we could add and then make a graph of what this titration would look like. And then we'll switch from strong to some weak strong combos. Alright, so I want to look at these points. We just did this one, the 50, when we find the pH to be 7. Alright, so I also want to figure out what was the pH before I even got started. So here, volume of HCl added is 0. So what is in my flask before I start the titration, based on my amazing drawing? Right? That's the only thing that's in there. Right? So I want to figure out what is the pH if I just have 50 milliliters of sodium hydroxide. So alright, so do I need to use an ice chart? No. Right? It's a strong base. Do I need to convert it to moles? What am I looking for, right? I'm looking for pH. Is pH in molarity or in moles? It's in molarity, right? Because it has brackets. So what is something I could figure out right this second if I have 0.1 molar sodium hydroxide? The POH. Doesn't matter what volume I have. Not the strong acid or strong base by itself. Doesn't matter how much you have of it. So what is the POH of this solution? Negative log of 0.1. If you don't have your calculator out, again, handy to have. What does this equal? 1. Am I done? No. What do I want? I want the pH. So how do I find the pH from the POH? Subtract from 13. From 14, you get 13. Does that value make sense with what you know about bases? Yes, right? Super strong base. It should have a very basic pH. Good. Alright, so now I don't know of any strong bases that have a pH of 14. Yeah, not regular bases like we use. No. Alright, so let's make a guess. If I know if I've added 0, it's 13. If I've added 50, it's 7. What should this in-between point be then? Ish. Like probably 9, 10, somewhere in that range. Let's find out. But we expect it at least between 13 and 7. It should be in that ballpark. Alright. Alright, so now I'm saying I have added hydrochloric acid. So what should I... There's like 2 or 3 things I have to do right now when I use the word added. the IACE chart. Yep, I know for sure I need to have this. What's the other two things now I need? I need the title, right? I need the equation across the top. And then what's the other thing I have to find if I'm using an IACE chart? Moles. So either order. Let's figure out what the equation is first. What are the two things that are reacting in my flask? Right? Do I write them as HCl and NaOH? What do I write the NaOH as? Just OH minus. What do I use HCl? What do I turn it into? Just hydronium. Right, so that's my strong base and my strong acid making water. So in order to fill this in, now I have to find the moles of everything. So we already had moles of sodium hydroxide. We found that on Wednesday. It hasn't changed. I wrote that really tiny. Sorry, guys. How do I find the moles of hydrochloric acid? What do I know about the hydrochloric acid based on the question they gave me? I know the molality, and then I also know the volume, right? So I know it's 0.1 moles per liter. And then how many milliliters am I gonna, or how many liters am I gonna add of it? Right? 0.025. Alright, now we're ready to plug some things in. Let's see here. Alright, so now we get to the point when we did this on Wednesday, right, they totally canceled out. What is going to happen here? Yep. So it's a limiting reagent, right? You use up the one that's the least first. So I have to use up all the hydronium because that's the smaller amount of moles. Right, so the limiting reagent, you're going to use up the one that has the least number of moles first, just like we did in 108. Those guys all are disappeared. And now I have that many moles of hydroxide left. Alright, so when we did finding the pH up here, what units is this in? It's 0.1. Molarity, what units is this in? Moles. Can I plug that in the pH right now? What do I have to, alright, this is moles. Molarity is in moles per liter. So you have to stop and think and say, okay, in my original flask I had 50 milliliters. I've now added 25 milliliters. What is my new volume? 75. So this many hydroxides are now floating around in 0.075 liters. Now I have concentration of OH minus is, what is that? 0.063 molar. Alright, now how do I find the pH? Oh, question first. Sure. I find it's the easiest to look at my picture. When I started, I had 50 milliliters in my Erlenmeyer flask. And according to my chart, I have added 25 milliliters of HCl. So now my flask has 75 milliliters. We'll do a bunch more of these. You can pick up on how to do that. Alright, so now I have concentration of hydroxide. So now I'm going to do it exactly like I did this part up here. Right, I'm going to find the POH. Is this a reasonable pH? Does it fall between 13 and 7? It definitely doesn't decrease as much as we thought it would, because that strong base, there's a lot of strong base eating up all those little hydroxides, or hydroniums, making little hydroxides. Questions on that before I start sketching the graph? Okay. So we're going to call these titration curves. Alright, so when you do a titration curve, pH is always on the Y. And for our class, volume added is going to be across the X. And obviously the volume added is going to be the thing that changed. So it's either going to be, in our case, for this problem, it's volume added HCl, right? That's the thing we are adding. What should the scale on my y-axis be? Top and bottom. 0 to 14, right? Seems like a trick question. So when I added, and again, this is going to be 0 to milliliters. When I added 0 volume, what was the pH? 13, right, we're up here. When I added 25 milliliters, it was 7, a little bit less than that. And at 50 milliliters, it was 7. Obviously, it's not a great curve, it only has 3 points. What would you expect the pH to be if I added more than 50 milliliters of acid? Greater than or less than 7? Less than. So we expect the curve to continue out. It'll look something like that. So a good titration curve, look, whatever shape that is to you. This. Like a cobra about to strike. Or some Donald Trump hands. Something like that. Right? I mean, that's what it is. No? Maybe people don't watch The Apprentice anymore. Yes. Yeah, so in this case it was acid being added. If I had the opposite, if I was doing base, it would be you end up at a high pH. Alright, how about we do a bunch more of those? I know it's the day before spring break, you guys are so pumped. My slides are all out of order, hold on. Oh, here we go. Alright, so that's all. Bless you. So let's look at, that was a strong acid, strong base, and those are going to be fairly standard. Let's look at a weak acid and a strong base, and then we'll do the opposite. Do a weak acid, strong, no, weak base, strong acid. So anytime it's a weak, strong combination, there's going to be 3 important points to a titration. So the pH before you add anything is going to be calculated from the weak acid, Ka, and the acid concentration. Alright, so it's going to be this problem that we've done a bunch of times, where if I have 50 milliliters of 0.3 molar weak acid, what's its pH? Set below ice chart, solve it out. You can figure out the pH. pH at the equilibrium point can be calculated from the conjugate base acid combination. And the pH at the half equilibrium point is equal to the pKa. Because that's the point where moles of conjugate base equals moles of conjugate acid. Alright, so let's do a practice problem where we look at these 3 points and figure out how the pH changes over time. Oh, the half equivalent point is also sometimes called the midpoint. Midpoint in titration. That's only important because on my next question I asked about the midpoint, and otherwise you wouldn't know what that is. Alright, let's say I have a 25 milliliter sample of 0.1 molar NH3, and it's being titrated with 0.1 molar HCl. Before we even get started, I want to draw a picture of what's going on so you can keep track of what is where. Okay. So the question says you have a 25 milliliter sample of ammonia being titrated with 0.1 HCl. What is in the flask? 2 options, right? And should be 25 mils of NH3, and the HCl is being added to it. Okay. Now we're going to look at the 3 different points along the titration and see how the pH changes. What is in the, I gave you the title in this case, but what's in the flask? The weak acid, weak base, strong acid, strong base, NH3. Weak base, right? So what would we expect the pH to be before we get started? More than 7, less than 7. More than 7, right? So we're going to expect the pH to start off above 7 and eventually end up below 7. Alright, so let's take a look at some of these. I was going to say this is not nearly enough space to do this problem. We're going to need some extra paper. Alright, so A. What is the pH of the solution before the titration even begins? Alright, so I have my Erlenmeyer. I haven't done anything to it yet. It has NH3. And what in it? Water, right? It's NH3 and water. Yep. It says there's nothing else in it, so it's NH3 and water, right? Because it's in, I guess it's an implied aqueous solution. Alright, so if I have NH3 and water, what is one of my products I have to make? NH4 plus. And then what's left? My hydroxide, right? Which makes sense, it's a weak base. We have to have hydroxide. Alright, is this a buffer at this point? It is not a buffer, right? Because it only tells you that there's NH3 in there. I would have to, if it's a buffer, I have to tell you there's 2 ingredients. It is not a buffer yet. It's only NH3. If I only have NH3, what sort of chart do I need to make? just a boring ice chart. It is not a buffer because it's only one reactant in my flask. So just a plain ice chart. What units are plain ice charts done in? Molarity. Okay. Alright, so based on the information in the table, right, put 0.1 there. Alright, we're now ready to start solving. My throat. I'm sorry, my voice is cracking. It's crazy sounding. Do you now need a Ka or a Kb? You need a Kb, right? Because it's a weak base. Kb is 1.8 times 10 to the negative fifth. X squared. What assumption can I make about this denominator to help us out? Right, the x is small. So I'm just going to put 0.1. That should be much faster to solve. The 5% rule. So what you would do is say if it's 5%, 1.3 times 10 to the negative third divided by 0.1 times 100. Right, definitely under the 5% rule. Alright, so now, can I find pH right this second? Sort of. Indirectly, I can figure it out, right? So this is OH minus. I like to find the POH and then subtract from 14. To me, that makes more sense. This. I did 1.8 times 10 to the negative fifth times 0.1 and square rooted. Yeah. For those playing along at home, get something similar. Okay. Does this pH make sense with the fact that it's weak base floating in its flask by itself? Hanging out, just deprotonating. No. Okay. Alright, so that is where this titration begins. I now want to look at the pH at the equivalent point. So if I look at the pH of the equivalence point, let's think about what that means. Correct. For anything else, you have to calculate it. All right. What is chemically true at the equivalent point? Yep, moles of conjugate acid equal moles of conjugate base. Okay. All right, so moles of conjugate acid equal moles of conjugate base. That's true at that point. So in order to figure out where that is, what do I have to find? Moles of, which one do I know right off the bat? NH3, so it's at the base of the acid. I can find moles of base right now. let me do that first. That's what we say. 3.1 per liter. Alright, so I know initially I have that many moles of base. At the equivalence point, how many moles of its conjugate acid should there be? The same. Okay. So what volume is that going to happen at? So I have this many moles of NH4 plus. Right, and that comes from adding the HCl. So the volume that occurs out is calculated from the molarity of the HCl, right? Because that's the only thing you're adding. Right, we're not adding any actual NH4+, we're adding HCl. And every HCl you add converts an NH3 to an NH4+. Okay? So if I know I want that many moles, what do I know about the HCl that I can then figure out liters? I know the molarity, right? Right, so I have to add 25 mils of HCl. Alright, we are almost done setting up the problem so we can solve it. Getting close. Alright. So now, let's think about what the chemical equation is that's going on in solution. Is this a plain ice chart or an IACE chart? It has to be an IACE chart, right? Because I'm adding HCl. Do I do that in molarity or moles? Moles. Okay. What IACE chart's always in moles? Is what's going together. So what are the two reactants in my flask now? What two things go in? The NH3 and the HCl, but how do I write that? H3O+, right? So in my flask, these are the things that I have. Which will make an NH4+ and a water. Almost about. Because it's a strong acid, and it's going to make all these hydroniums. You could write it as H+, but then it won't balance as nicely. right? Because HCl breaks into an H plus and a Cl minus. We don't care about the Cl. Make those H pluses. I just always write them as this, so it's easier to balance. Alright, so I know moles of this. Initially there's none of that, and that's just water. What am I adding? HCl, which I write as H3O+. So I'm going to add this much. Alright. Where do I add? Do I add to products or I add to reactants? Products, right? I'm going to add and subtract off of this side. So how much NH3 am I left with? 0. How much hydronium am I left with? I'm left with all NH4+. Can you find pH knowing the NH4 moles? Directly? No. All a bunch of quizzical faces. No, you can't. In order to find pH, what units do you have to first be in? Molarity, which is why we need to know the volume. So what's the total volume in my flask at this point? 50 milliliters, right? I had 25 to begin with. I know I need to add 25 more. What is that? 5.0. Say that again? Moles. Right, because that's moles. Yeah, that's moles, and if I divide by liters, I'm in molarity. Moles per liter. That's what I'm doing, I'm dividing. Sorry, shorthand. I'm taking that number of moles, dividing it by liters to make molarity. You can certainly write it again, but there's so much writing that I try to find shortcuts where I can. We're 3/4 of the way done with the problem. Alright, so I'm now at the equivalence point. I know concentration of NH4+. Can I find pH yet? No. What happens if I have all weak acid in a solution? Right, so if I wrote, you may need more paper. I now have all this. What do we do next? It's a double ice chart. Woo! The equivalence point has to have an IACE chart followed by a standard ice chart. So if you want to make a note for that, equivalence point titration problems require an IACE chart followed by an ice chart. Always. So pH at the equivalence point questions require the IACE chart followed by a standard ice chart. Always. I haven't decided yet. Because they're long to solve. Yeah, right. I mean, as it is, we have so many things on this test that to pick and choose, like, what are the things I really want you to be able to solve versus just be able to, like, set up. So, right, and so I have not written, let me say as my caveat, I have not written the test yet because I wanted to see how far we got at the end of this week. There's 2 more topics in Chapter 16. I'm going to not have them on this test. I'm going to put those topics on exam 3. They're very similar, that they use ice charts, but it's talking about supersaturated solutions, like how much solid can you put into a solution before it particulates on the bottom. We're going to hold that off to the next. So we're going to do just all acid-based on this test. So, So, we'll see. Writing a test is very hard, actually. Because you want to cover all this stuff, but you have to be mindful of how long does it take, how many multiple choice questions, how much do I want to grade, right? I could do it all as Scantrons, but then there's no extra credit, partial credit. Yeah. I could have 100 questions, each worth a point, or I could have 5 questions, each worth 20 points. So trying to figure out what's the best for everybody. Yeah. I just have 100-point question. And it's this, right? That'd be incredibly stressful. Yeah. I won't do that. Question. Oh, you're right. I'm sorry. Alright, so now we are ready to solve this to find the pH. So we just found the molarity. At this point, you should speed through these plain old ice charts, right? Those are the speedy ones. Alright, so now, if I gave you both a Ka and a Kb, which one do you need to solve the problem? You need a Ka now. I would say for all the titration problems, that is a very good assumption. If I'm doing a titration, it should always be less than 5% until we kind of get to the far end of titration. But, yeah. I mean, this one, right, you can kind of eyeball it. Unless the value you get for x is even within a factor of 10 of this number, it's not really worth testing, right? Because it is 0.05 compared to 0.000005. So look, I helped you out. That is the hydronium. How straightforward is that? Right? Alright, why don't we do the easy one? We'll do the equivalence point, midpoint. We'll do the midpoint, and LA have a quiz. Alright, the pH of the midpoint. Right off the bat, what's the pH of the midpoint? Not 7, because it's not a strong acid, strong base. It is pH equals pKa. pH equals pKa at the midpoint. I just told you the pKa. Now that one included some other stuff in it. Alright. We will do many, many more of those after spring break. Lots and lots and lots more. Maybe I'll switch it up. Maybe we'll have a weak acid with a strong base. I'm tricky.